Hello, learners. Today, I shall tell you about the iteration logic structure of our programming language. To follow my lecture in a better way, I would like to share some presentation during my lecture session. Let me give a few seconds to load my presentation. First, I shall tell you about the objectives of this lesson. The objective of this lesson is to illustrate the idea of repetitive execution of a set of code in a computer program till the user desires. The logic structure used for this purpose is called a loop structure. In the literature of computer systems, the structure is known as the iteration structure. The logic structure is inevitable in computer programming because most often we require the repeated execution of a part or whole of a set of programming statements until we meet our requirements. The concept behind the loop structure. The control logic structure is used in a computer program to perform a repetitive task is popularly known as loop structure. It is used when we require executing the same set of codes for some desirable number of times. The desirable number may also be kept infinite or indefinite depending on the user's choice during the execution. Choice or need, we can say. There are two forms of iteration, namely pre-test iteration and post-test iteration. In case of pre-test iteration, a predicate, commonly known as a condition or conditional expression, is checked first. If it evaluates to true, only then the set of statements under the structure is executed. In case of post-test iteration, a set of statements under the loop is executed first, and then a conditional expression is checked to decide whether the repetition is to be done or not. Thus, the statements in the post-test iteration are executed at least once. On the contrary, the statements under the pre-test iteration may not be executed even once, because a condition is to be tested before entering into the set of codes that is to be executed repeatedly. If the condition is found to be false, control does not enter into the execution of the code set. That is why the code set may not be executed even once. I have shown here the flowchart depicting pre-test iteration. After the start of the program, there may be some inputs if required. These inputs are accepted from the user, or there may be some assignment statements, or after the inputs, there may be one or more assignment or processing statements required. After that, we need to test some predicate or conditional expression based on which we shall we execute a set of statements. This set of statements is executed if the predicate is found to be true. Otherwise, control goes out of the repetitive set of statements and it comes to next set of statements, if any. Otherwise, it completes the execution. If there is any set of statements after the condition is found to be false, control is therefore either comes to an end or executes some other desired set of statements outside the loop and then comes to the end. This is the pictorial presentation of pre-test iteration. Next comes a flowchart for post-test iteration. In case of post-test iteration, after the start, inputs as usual are accepted if required from the user. Then there may be one or more assignment or processing statements There may not be any processing statements. After accepting the inputs, we may directly come to a set of statements to be executed repeatedly. After first execution, first round of execution of the statements mentioned here in this step, a predicate is tested. The conditional expression is tested. If it is found to be true, then the set of statements are repeated. This is a connector, R is a connector. It connects to this point, meaning that the control comes back to this set of statements for next round of execution. And this goes on until the predicate becomes false. Otherwise, when the predicate becomes false, in that case, control comes to an end, or as I showed in the previous case, there may be a set of statements to be executed before coming to the end. I have not shown the set of statements in this case. This is the post-test iteration. Pre-test iteration. In case of pre-test iteration, let us talk about R. R supports two structures for pre-test iteration as stated below. First one is while structure. Its syntax is like this: while conditional expression followed by a set of statements to be executed repeatedly within a pair of braces. If the set consists of a single statement, the pair of braces is optional. Another loop structure is this for loop structure. For some expression is to be given here that I shall explain more elaborately later. And if the expression is found to be true, on the basis of that, set of statements to be repeatedly executed are written next within a pair of braces. For a single statement, as earlier I have stated, the pair of braces is optional. The actual syntax of the loop structures are shown below. Actually, the basic syntax for creating a while loop in R is as shown below. While conditional expression to be tested, set of statements, R set of statements to be executed. As I have shown here in an example, count. Suppose I have assigned the value 1 to some identifier or variable, R variable count. Next, I've asked R to check whether count is less than or equals to 5. In this case, it is of course less than 5 because R is count, the value of count is 1. So the condition becomes true. Then it comes to the next statement. It shows this: welcome to R while loop. After printing this line, the count is increased by 1. We have written this by using, we have shown this by using count, by writing what? Count equals to count plus 1. Count is increased by 1. And the increased value is stored in count. As the brace of the loop is completed here, the control goes back to the starting statement of the loop. Actually, it goes back to the starting statement while structure. It again checks for the value of count. As the value of count is now 2, the condition is again satisfied. Again, this printing is done. Again, the value of count is increased by 1. And this goes on until the value of count becomes greater than 5. And it is obvious that this statement, this text, welcome to R while loop, will be printed 5 times by taking the value of count from 1 to 5. After 5th time, count becomes the value of count after incrementation of 1 becomes 6 and control comes out of the loop. And this can be shown by writing the code in some R environment. Let me show you the environment here. Let us load R. Let me refresh the screen. R is here. Icon is here. I'm loading R here. Now R is being loaded. So it has loaded now. So to see the things that we write here in a larger font, I'm changing the size of the font. Let me change the size of the font to 20. Make it okay here. So it becomes better visible. So we can write the whole thing here one by one, or we can create a new script here by selecting new script option on the file, as I showed earlier also. So we have written here, but the quotation signs here are not acceptable in this text editor, because these have been copied from a PDF file. So we have to change these quotation marks. I have changed the quotation marks. Now I can run this code by enclosing the whole thing within a pair of braces, as I shown earlier also. Next, I select edit and run all option. It runs, it has run it. Now how to see the output of this run? Now we can make this smaller and to see the output. We see that the welcome to the state text, welcome to our while loop, has been shown here 5 times. After that, control comes back to the R prompt. Let us go back to our presentation. So here I've shown that all these statements written above can also be written in a single line, as I've shown here. Let me copy this in the R prompt. I see. Actually, there are something more things copied. So let me put it here first to eliminate the extra things copied. This is the extra thing that I have copied. Another thing is what? Count is, this is okay. Print, this codes have to be changed here. Then comes what? Let me increase the size of this. Then we need to change this symbol, this symbol, then these double quotes as earlier. Then we write what? Oh, this is an extra statement that we have written here. That is not needed. Count equals to count plus 1. So this is all. Now this is the start of the loop. This is the end of the loop. As more than one statements are here, we have separated the statements by a semicolon, and we have put both the statements under a pair of braces. So we can now copy this whole thing. I'm cutting it, cut, paste. Let me paste it here at the R prompt to execute it, to execute this here. It is showing error because the text copied is meaningless actually to us. That's why unexpected symbol by prof, doctor, etc. Now let us see this one. So again, it has been executed, and we have seen we have got the same output, same result here. Oh, I see what is being done. It is being continued indefinitely. I think there is still some error in my code that I have written. Let me check it. Why is the error? Oh, I have got it. It is a never-ending loop. Let me stop this. Just close R to stop this right now. I shall see it later. Stop current computation, we can run. Save workspace image, no. So, yep. Has been, what do you want to save this change? Yes, save it. Okay. There is an untitled file that I showed earlier. That is what example of while. Okay. Ellie, say. Okay, let me load R again to check the mistake that we encountered in the earlier statement. So let me check the size here and change the size to 20 or more than 20, 24. Okay, so let us check this. Oh, what was that? It has been, no, it was, let me copy it again from my PDF file. What was there? There was definitely some mistake. I've copied it again. There may be mistake in our coding. That is a part of coding, part of the task. So if there is any mistake, we can rectify it. We have to go through it and rectify it. So let us put it below. Okay. What happens? Count equals to 1, it is okay. While count less than equals to 5, do this. We change this code. What happens? Welcome to R. Code this also. Single quotes. Then this semicolon. After this, count equals to count plus 1. So these two statements are under this. So I think nothing else is here. Let us cut this and we bring back the arc also. So let us check it again. Count is being increased by 1 each time. Let us check what happens. It is being run. The loop is not stopping. Oh my God. What is this? That means there was some stop current execution. We have stopped it. So let us check it. What happened there? Including this. While R less than equals to 5. R is being increased. Count is this. Count capital. C capital. Count while. Count less than equals to 5. Print. Welcome to R while loop. Count equals to count plus 1. It's strange. Print this. It should not go beyond 5. Print is this. control comes back to this point. I think some embedded error is there. So let us type it afresh. Count equals to 1. Count is set to 1. Next we write while count while count has been spelled with C small, not an issue. Earlier we spelled with C capital, not an issue. Count less than equals to 5 till this remains true. It should execute this print what to print this what is this, what did I welcome to. So we write welcome to our while loop single double bracket. Okay, welcome to this while loop. Okay, so this is printed. After that, a semicolon is required. After end of this print, after this semicolon, we increase the value of count by 1. Count equals to count plus 1. Now we complete this and then we run this. Now you see that our desired output has come now. So earlier there might be some embedded error, or it might be that some embedded error may be there, for which is beyond our notice actually, for which it was being executed repeatedly. Otherwise, it should not be the case. This is the case. So as I copied from a PDF file, there might be something creeped into this code that has been removed by typing it afresh. Okay, let us go back to this. Right. This is the output that it should show. Now, in case of for loop, for variable in sequence, set of statements to be executed repeatedly. Some variable is to be varied here following some sequence. A variable refers to any other variable used for taking a set of values mentioned by the sequence one by one to execute the set of statements written for repeated execution. Here, the increment of the loop variable will always be by 1. However, sometimes we need to increase the loop variable by any desired step size. For this purpose, the loop structure should be written as follows. A loop variable in sequence, seq, SEQ, it is a function available in R. Using this function, we can vary our loop variable from some starting value called beginning value to some ending value, each time increased or decreased by some step size, and followed by the loop statements within a pair of braces. Another point to be borne in mind is that R does not compare the initial value of the loop variable with the ending value here. So in this case, it starts executing the loop with the beginning value. If beginning value and ending value become same, then also loop will be executed once. So it executes the statements within the loop with the increased value, with the beginning value. Then it increases the value beginning value by step size. Then it compares the increased value, newly evaluated value with the ending value. If the ending value does not satisfy the condition, the ending value becomes smaller than the value newly evaluated. After the increment or decrement in step, the loop statements will not be executed. So this is what I have described here. R does not compare the initial value of the loop variable with the ending value to enter into the loop statements. It first executes the loop with the initial value, increments or decrements the value by the appropriate step value, and then compares the resulting value with the ending value before going to execute the loop statements for the second time to ascertain whether to continue the loop or to discontinue. The following code snippet illustrates this feature. Say we write I in sequence 1 to 0 minus 2 print I. This means what? I should start the loop with the value 1, then after execution of the statements in the loop, it will decrease the value by by 2, or it will increase the value by -2. That is actually decreased value will become. After that, the newly evaluated value will be compared with the end value or stop value. If the newly evaluated value is not greater than this or less than this, then actually here it will be, as this the step is negative, it is beyond this range 1 to 0. If it becomes beyond this range 1 to 0, then loop will be stopped. So here after with 1, it executes, it shows 1, then the value of I becomes is decreased by 2, that is I becomes -1, and as the value -1 is beyond this range 1 to 0, the loop will stop execution and will not get any more output. Another example. Let us illustrate for loop. Say s equals to 0. We have initialized some variable s with the value 0 by assigning the value 0 to s. Next, we have done what? We have used the capital I variable. Once we use capital I, once we write capital letter, we have to use always capital letter for any reference of this variable within this code. Okay, so I have written here capital I here also to imply the same variable. So I is to be varied from here. Well, what I have said, I should be varied from 1 to 10. In this case, the default incrementation is by 1 to 10. So 1, 2, 3, 4, up to 10. These values will be taken by I, and for each value of I, the age will be incremented by the value of I. That is, the value of I will be added to the current value of S. Initially, the value of S was set to 0. Now, in the first step, value of I, that is 1, will be added to this 0 value, and the resulting value will be stored in S. So S becomes 1 after adding 1 to 0. Next time, in the next step, S becomes 1. S contains 1, and the next value of I, that is 2, will be added to 1. That is 2 plus 1, S becomes 3, and that will be stored in S. And this will be continued until the value of I is more than 10. Okay, so the sum of the first 10 natural numbers is this. The sum of first natural numbers actually will become 55 in this case. A while loop that can be run for an indefinite period is illustrated below. While we can write while true. Actually, without writing any conditional expression, we can write the logical value true or capital T. This makes the statements within the loop infinitely executable. But we cannot run an infinite loop. We cannot run something for an infinite period. We write something to get some result. So after some period of time, after some number of execution, when our requirement is satisfied, requirement is fulfilled, we may like to come out of this execution. In that case, we have to put some control statement that breaks the loop, that breaks the repetition of the loop. That I have shown here. Cat enter the year to be tested. We have written the prompt to we have written the prompt to the user to enter some year for testing as leap year or not, we have also given the prompt to enter 0 to terminate the code, to terminate the loop if we don't want to continue anymore. So now next the year is accepted. Next, as an integer value, we have specified what equals to integer bracket. Next, if y is found to be 0, when the input is given, then the control will break, and otherwise it will check this. If y modulo, this is double percentage modulo about y modulo 400 is equals to 0. I showed this logic earlier also in case of selection logic, where I explained these things. A year is checked against the divisibility by 400. If the year is divisible by 400, we can conclude that the year is a leap year. Otherwise, we need to check the year. We need to check whether the year is a century year or not, like 1900, 1700, etc., 1600, etc. If it is a century year, non-century year, then only we check the divisibility by 4. If it is a century year, in that case, actually, 400 will check it. So if the given year is not divisible by 4, 100, but divisible by 4, that means what? A non-century year being divisible by 4 should be a leap year. So in that case, we shall say it is a leap year. Otherwise, we shall show it is not a leap year. In place of true, we can also write any number, any whole number other than 0 to continue a set of statements to run forever, or to run for an indefinite period, or to run for any number of times with TCL until a given until actually given condition is satisfied to break the loop. Until it encounters the break statement, the loop will be continued in that case. So I've written the same thing by using this while loop. The same thing. Here I've written while 2, here I've written while 1. In place of 1, I could have written 2, 3, 4, any number, but not 0. If I write here 0, it means what condition is initially false. So control will not enter into these loop statements. So we can test this by copying this statement. Let us copy these statements in our environment. I've copied the whole thing. There is some code here, quotation sign. So let me change those codes. You know that these codes are the quotation marks of PDF file. So they will not be applicable here. Next, y equals to 2, you understand what equals to integer, you understand, I explained these things earlier. If y equals to 0, break. Otherwise, we check the condition for leap year. So let me copy this also and write it beside this statement. Okay. Again, here there are some quotation marks which are to be changed. Okay. So let us press enter to run this. Enter the year to be tested. Enter 0 to terminate. Let us give our this year 2023. You know that this is not a leap year, so it should show. It is not a leap year. 2000, year 2000 was a leap year, so it is a leap year. Coming year 2024, I think you know that it will be a leap year. So it is a leap year. In this way, say 1900, although 1900 year is divisible by 4, but it is a century year. So divisibility by 4 is not enough. It has to be divisible by 400. So it is not a leap year. So 1900 is not a leap year actually. 1600, it is a leap year. 1700, it is not a leap year. So we have tested a lot of years. So now we don't want to test anymore. So I enter 0 here to terminate the code. It has been done. I think it is very simple. Next, we shall come to another logic structure, that is a repeat loop structure. There is no loop structure in R strictly following the definition of post-test iteration. However, there is a third loop structure in R that may be used in that format to some extent, depending on the way how the user utilizes the loop structure. This loop structure is known as repeat loop structure. Truly speaking, the repeat loop is a never-ending loop, that is an infinite loop. But there is a control statement in R that can be used to come out of the loop at any point of time. It is the break statement. I've shown the break statement, use of break statement in our while loop also. This statement is usually written under a conditional statement to break the repetition. If this conditional statement is written just before the ending brace of the loop, then only we get the flavor of the post-test iteration. In general, the loop structure can be demonstrated by using the flowcharting symbols as shown in the figure below. Start of the repeat loop, statements to be executed. Now we can check some condition of predicate here. If it is found to be true, the control should go back to the start of the repeat loop to execute the statements or to repeat the execution of the statements here. Otherwise, if it is that is when the predicate is found to be false, it will exit from the loop. And there may be many other statements under after this exit from the loop. In terms of R, the structure can be written as follows: repeat set of statements to be executed repeatedly. There is another control statement in R that is often used in a loop. It is the keyword next, very important keyword next. When the R system encounters the next command, it suspends execution of the remaining statements in the body of the loop, goes back to the beginning of the loop, and starts execution of the loop statements afresh. In case of a for loop, it continues the execution of the loop with the next value of the loop variable in case of a for loop, if any. Thus, the keyword next functions as the continue keyword available with some programming languages like C. Otherwise, it will normally continue from the beginning of the loop if it is not a for loop. Let us have an illustration of the repeat loop structure as in the script below. Count 1, the previously written code, actually count 1, repeat, print, this is the repeat loop. Count equals to count plus 1. So let me check this. Let me copy this statement from here to here. So you know that we need to change these quotation marks. So I change this. So count equals to 1, repeat loop starts, print, this is the repeat loop, then count is increased by 1. Count equals to count plus 1. I think there's some more statement here. Yes, if count is greater than 3, we have asked the system to break the loop. So let us include that also. So if count is greater than 0, we break the loop. So let us run this. You see, now there is no embedded error here in this statement, although it has also been copied from our PDF file. So it has the loop has run for 3 times as expected. When after showing this message 3 times, showing this text, this is the repeat loop text 3 times, the value of count becomes 4 and control will come out of that. Now, I shall show you the use of some next statement, example of a next statement in a for loop. For I in x, if I equals to 3, next, otherwise print. That means what? When I becomes I in x, what is x? I don't know what is x. So x must be available to the system. I don't know what is x. So in that case, we should define x like this. X equals to 1, 2, 5, or whatever it is. Now, let me copy the statement here for I in x. For I in x, if I equals to 3, next, otherwise print I. So you see, I has got 5 values, 1, 2, 3, 4, 5. When I is 3, it goes to next statement. That means the next value of I is taken. So 3 is not printed. Control goes from this next statement, it goes back to the for loop. It increases the value of I and takes the next value, and then it prints this. So that is why 3 is not printed. Let me show you another example with this use of next keyword in a while loop. So it can be shown in case of a repeat loop also. Similarly, in place of while, we can write repeat, same thing. It is a long statement, a very big statement, while 1. So let me change these things first. Enter any positive number. After while 1, there is no brace. I think brace was not given here, but there should be a brace. There should be a brace because we would like to write some more things. Brace is missing from here. Okay, whatever it is. During writing, actually, the brace was missed. Next, we accept the value. We accept the value. For accepting the value, we write num equals to scan, n equals to 1.2. If num equals to 0, break. That means what? If num equals to 0, break, it is okay. After this prompt, what happens? We accept the input, then we check whether the input value, given input is 0. Otherwise, if it is 0, the control should break. Otherwise, it should show something else. If it is negative, we want to print this invalid input, try again. We want to print this. So let me write that. If it is 0, we write this invalid input, try again. So 2 statements are here. When there is more than one statement under this if num equals to 0, print statement and next statement, we must put these 2 statements under a pair of braces. invalid input, try again. Okay, then next, then we complete this base. So these two statements are under no negative value of num. Otherwise, what to do next? Otherwise, we want to show you have entered this number. Otherwise, the system will show you the number that we have entered. So write that. Now, let me change these quotation marks again. Then this is for new line characters, quotation marks, and this completes our while. So starting brace after while is completed here. So let us run this. A long statement is here. Let us run this. Error. While one. Unexpected symbol in while one. What is this? While one. Enter positive number 0 to continue. Semicolon. Again, something is wrong. Enter this positive number 0 to continue. Semicolon. Num scan. If num equals to 0, break. It's okay. Oh, num 0, break. Okay, okay, not an issue. Or not an issue. If num is less than 0, if num is less than 0, invalid input, try again. It's also okay. Then comes what? Brace. Then comes what? Cat. You have entered what value? This value. There is invalid input, try again. Next. After this cat, not an issue. I can just change one thing. The semicolon after next can be given just before cat. Nothing can be changed. Nothing is required to be changed. Otherwise, it is also okay. Let me check this. I have written nothing wrong here. Oh, I see. Yes, yes. No, it was not copied. I have written that in the previous line. It's okay. It's okay. Now is there. One thing that I can do is this at best. After next, we write semicolon here, and nothing else can be changed. Next and invalid input should come together. Then break. If num is 0, break. Otherwise, it will accept the value and it will show the value. Try again. You have entered this value, num. Yes, it is only for that actually. It will keep an error. Okay, enter any positive number. Say, let us give 67. It is showing you have entered 67. Let us give some negative number, 45 minus 45. What happens? Invalid input, it checks as expected. Try again, enter any positive number. We don't want to enter any more positive number. We have tested it. Okay, so let us go back. Similarly, we can use the keyword next in a repeat loop structure. I told you. I can show it in some other statement also. Now, this is the program to determine the sum of even numbers. It is very simple. We want to find out the sum of all even numbers starting from 2 until the sum exceeds 1000. And that is the condition will be on sum. So we have written this. we have set the number, initial number to 2. N is the variable to represent the number that are to be added. The S is the variable where we want to hold the sum of the even numbers that we have generated. CNT is a variable to count how many even numbers are being added. That is also demanded here. It is required to obtain the sum of consecutive even numbers starting from 2 until the sum just exceeds 1000, and then to show the sum and the number of even numbers added. So we need to show sum as well as the number of even numbers added. To get the sum, to accumulate the sum, we have defined S with initial value 0. We have defined to get the count of the even numbers added. We have defined the variable CNT to get the counter to 0, initial counter to 0, and to set the initial number to 2, first even number, we have set n to 2. Now, our condition will be on the sum. Sum must be less than or equals to 1000. Till then, the repetition of addition and counting will be continued. So, if while sum less than or equals to 1000, we add the current value of n to S and put it in S. Then current value of initially the current value of n is 2, S contains 0, 2 plus 0, so S contains 0. And as we have added one number, counter is incremented by 1, count equals to count plus 1, that is we add 1 to the current value of CNT, current value of CNT is 0, we add 1 to 0, so CNT becomes 1, and that is stored in CNT. Now next n, to get the next even number, we increase the value of n by 2. And the process is repeated until the sum exceeds 1000. After that, we can show the sum that we have obtained that is being stored in S. And after that, we can also show what we can show. We can show what we can show the. We can show what we can show. The number of even numbers added. That completes our task. It is required to obtain, next problem, it is required to obtain the reversed form of a given number by using some R script. So reversed form of a given number. We can obtain the reverse, if we get the digits of a number, we can obtain the reverse form with the digits one by one. Suppose 1, 2, 3 are the digits. So first digit into 10, 30, first digit, if the variable with the old value, we can use this, say, variable with the old value. Let us set the variable with the old value to 0 initially. Now, first digit is 0. The first digit is 3. 123 we have given as input. So, variable with the old value is 0. 0 into 10 is 0 plus current remainder. How can we get the 3 out of 123? By dividing 123, the number, by 10. The remainder is 3. So current remainder is 3, and that is added to the variable with the old value. So in that case, 0 plus 3, variable becomes what? 3. Next time, we change the number from 123 to what? The quotient of the division by 10, integer quotient. What is that? 123 when divided by 10. The integer part of the quotient is 12. Again, we obtain the remainder by dividing it by 10. That is 2. We get 2. Now, variable contains what? 3 now. Previously, we stored 3 there. 3 into 10 is 30. 30 plus current remainder is 2. That is 32. That is stored in the variable. So, variable becomes 32. Our next, the result of integer division becomes 1. 12 integer division 10, it gives us 1 only. When 1 is divided by 10, we get 1 as remainder, and This variable now contains 32. 32 into 10 is 320. 320 plus the remainder 1 is 321. So we get the reverse form of value of the value. 123 becomes 321. Now we can show this in this way. Any whole number we accept here by using the prompt cat. Then we accept the number in n. Next, reverse number. For getting the reverse number in some variable, we define the variable Rn to be 0. And to get the count of digits in a number, because we may not know how many digits are there in the number. It may not be a 3-digit number, it may be a 10-digit number, 20-digit number, whatever it is. So we need to count how many digits are there in the number. And also one thing, there may be ending zeros in the number. If the given number is 100, the reverse form of the number should be shown as what? 001. If we use the logic that I have shown here, this logic, those zeros will be lost, because in that case, 0 added to any number will not increase the value of the number that I showed you. Addition of current remainder. 0 becomes remainder. If 0 is added to any number, the value of the number is not changed. So that is a task to be performed here in a different way. That's why you need to count how many digits are there in the number. So we set up this loop, while loop in this way. While n greater than 0, we find out the remainder from the number where it is divided by 10. It gives us the last digit of any number. Suppose our number is 1, 2, 3, 4, 5. So the last digit here is 5. If you divide the number, whole number, any whole number, by 10, the last digit is given as remainder. So R now contains the last digit. If R is 0, we count actually how many zeros are there. If R is 0, remainder. If the remainder is 0, that is if the number happens to end with 0, in that case we count the number of zeros. Otherwise, we just add the number to reverse it. Now, this is the integer division operator, %/%10. I told you about if your number is 1, 2, 3, 4, 5, the next in place of the number, we shall store what? The quotient of integer division of the number by 10. So we shall, next time we shall deal with 1, 2, 3, 4, and so on. So what happens here, in this way we have reversed the number, but we have also counted if there is any 0, how many zeros are there, because addition of 0 as the remainder will not make any change. So now because of the zeros, if count is greater than 0, that is number of zeros is greater than 1, we need to do something. We do what? We convert the reverse number in character form by using the s.character function, and then we run another loop. While CNT is greater than 0, we add zeros before, we add zeros to the left-hand side of the reverse number, 0. For this, we use the paste function. Paste 0 with Rn. 0 will be added to the left side of Rn. Separator, this is null, that is there will be no separator, and all and after this addition, after this concatenation of 0 with the reverse number, what will happen? A whole number will be generated, and there will be no gap in the digits in the number, and CNT is decreased by 1 each time. So if the number ends with zeros, the number of counts, the number of zeros will be added there. The reverse number is then can then be shown as Rn. Okay, so next problem. Our next problem is what? To show the divisors of a given number. This is a very simple problem. We know that a number can have a divisor other than itself from 1 to half of the number, because after half of the number, no other number can divide the number except itself. So we start division from 1 to half of the number, and the variables, the various values of I divides n here. If the remainder of division happens to be 0, only then the number is printed. This gives all the divisors except the except the number itself. As the number itself is also a divisor, finally we print the number itself to get all the divisors of the number. Next, we may like to find out the perfect numbers. A number is said to be a perfect number if the sum of its divisors except itself equals the number. For example, if a number is 4, the divisors of 4 are what? What are the divisors? Except the number itself, except 4. The divisors of 4 are 1 and 2. Sum of 1 and 2 is equals to 3, not equals to 4. So 4 is not a perfect number. Let us take another number, 6. The divisors of 6 are 1, 2, 3, except 6. So sum of 1, 2, 3 is equals to 6. So sum of the divisors except the number itself equals the number. So 6 is a perfect number. Now it is required to develop an R script for testing a given number as to whether it is a perfect number or not. So the thing is very simple. We accept a number and we scan it, its value. Then we do what? We obtain the sum. To obtain the sum of the divisors of the number, we initialize a variable with the name sum to 0, and then we check we vary variable I from 1 to half of the number, because after half, only the number itself can be the divisor. I told you earlier also. So number modulo I, if number modulo I equals to 0, that is, if the current value of I divides the number, the remainder becomes 0. If it is 0, that means what? I is a divisor of the number, so I is added to sum. The value of I means the value of I is added to the value of sum, and the resulting value is stored in sum again. This accumulates the total sum of all the divisors of the number. Now, after this completes the loop, there is a loop here. This completes the loop here. And after coming outside the loop, we check whether the given number n is equals to the sum that we have obtained. If it is equals to that, then we say that the number is a prime number, perfect number. Otherwise, it is not a perfect. That's very simple. Narcissistic number. If an n-digit number is equal to the sum of the nth power of its digits, n-digit number, it should be nth power. N is missing here, okay? Nth power of its digits, it is called an n-narcissistic number. It is also sometimes known as Armstrong number. For example, 153 is a number. For example, here it is a 3-digit number. So if we raise the power of each of the digits here to 3 and take the sum of the values with raised powers, we should get back 153. If we get back 153, we can call 153 a narcissistic number. We can say that we can also say that 153 is an Armstrong number. So 1634, 5588, 34 are such numbers, Armstrong numbers. So for this task, we have again used the cat function here to show the prompt, and then we have accepted an input. Now we have stored the value of the input in some other variable n, because the original number will be required later. Now we check how many digits are there in the number, as I have shown in the earlier section, in the earlier solution. And next, after checking the number of digits in the number, we declare a variable with null values, string variable with null values, with nothing. Then we set a variable tot to 0, and the n, as here in this division process, n becomes zero ultimately. So we put the value of m to n to replenish the value, the original value in n now comes back. Now we do what? We store the value of d in t. But why? Because we shall see it here. We shall we have counted number of digits here. Now the value of each of the digits, separated digit, when the you know that digit of a number can be separated, all the digits can be separated by dividing the number by 10. The last digit is separated, then the number is changed. That I explained in the last problem also. Then we have divided the number to obtain the remainder. Divided by 10 to obtain the remainder, that is n modulo 10 gives r. So now r to the power d is required. The following 5 lines of code may be omitted by a novice programmer. It is to show the digits raised to the desired power, sum up to the given number. Actually, we can. So that's why we have stored value of d in t. T is reduced by 1 here. Then we paste r to the power. We have shown all the values. This to the power this is this. Else we have shown this to the power this to the power this is this. Also concatenation. The 2 types of concatenation is there. We have concatenated the values. Finally, if the number m original number is there is equals to dot, that holds the exponential sum of the exponential values of the digits of the number, then we say that it is an assisting number. Otherwise, it is not an assisting number. Next problem is what? A sequence of numbers is said to follow the Fibonacci series if the first 3 terms are 0, 1, 1, and the subsequent terms of the series can be obtained by taking the sum of the preceding 2 terms. It is required to develop an R script to generate any desired number of terms of the series. Now, finding Fibonacci number is a very easy task. First 3 terms are 0, 1, 1. So we have initialized a variable with 0, another with 1, and we have accepted the input from the user, how many Fibonacci numbers we want to see, and then the Fibonacci terms are shown below. We have run a loop from 1 to n. Each time we print the value of t1. The current value of t1 will give you the term here. The t1 is 0. Next time t becomes 0 plus 1, 1. T1 we assign the value of t2 to t1, and the newly obtained number t to t2. Because the newly obtained number is what? T is the sum of the preceding 2 terms, t1 plus t2, as defined by Fibonacci series. So this continues the showing n times, and we get all the n Fibonacci numbers of the series. The next problem is a very important one, because it is required to test whether a given number is a prime number or not. Now, students sometimes do a lot of division or determination of prime numbers. We need not perform so many divisions, actually. It increases the complexity of the algorithm or the process that we adopt to determine whether a given number is a prime number or not. So I explained the logic here. We know that a whole number is said to be a prime number if it has no other divisor or factor except itself and unity. As 1 has no other factor except itself, it is excluded from the list of prime numbers. So everybody should remember that 1 is not a prime number. So we are required to test from 2 to the given number to determine whether it has any other factor except 1 and itself. Since 1 and the number itself are the common factors of all numbers, we need to test for other factors, if any. We need not test for 1 and the last 1 and the number itself. Also, we know that if a number has any factor at all, then at least one of the factors must lie within the integer part of the square root of the number. That is, for example, if say we need to test whether the number 97 is a prime number or not. We need not test from 1 to 90. We need not divide for testing the number 97 by taking numbers from 2 to 97 or 2 to 96. The square root of 97 is integer part of the square root of 97 is 9. So we can check it by dividing from 2 to 9. If we do not get any factor within that limit, within that range, then we can say that 97 is definitely a prime number. So we can confine our checking from 2 to the integer part of the positive square root of the given number. If we do not get any factor or divisor within that range, we can safely conclude that the given number is a prime number. R provides us with a SQRT function to find out the square root of any real number. We can reduce the number of divisibility by checking further by considering the odd numbers after 2 only, because if a number is not divisible by 2, it cannot be divisible by any other even number. We make use of these logical points in the following R script. We define an infinite or indefinite loop by setting while 1, and we have set some variable, say flag to 0. It is to actually check the status of divisibility. Initially, we set flag to 0 to set what? To set the number, no number is divisible by any other number, that is the given number has not got any factor. We set it to 0 initially. So we accept the number first, and if the given number is 0, we break the loop because it is an infinite loop with while 1. So we have to make it finite by including some condition of this form. Okay, so if num is 0, it will break the loop for loop. Otherwise, it will check from 2 to square root of the number. Here, as we are considering integers, here square root of the integer part of the square root of num will be considered. Now we check if the number is greater than 2 and it is divisible by 2, then we go to next. We need not check other numbers which are multiple of 2, because those numbers will be even numbers, and even numbers other than 2 cannot be prime numbers. That's why you are omitting. To omit those numbers, we have written this code. Now, I is being used as a divisor. I'm showing this is for user's perception. I've written which number is being used as a divisor to show that if the given number is not is divisible by I, then that means what? The number is not a prime number. In that case, we set the value of flag to 1 and we break the loop. Otherwise, we continue the loop with remaining values of I up to the square root of the number. When we come out of this loop, we can check the value of flag, whether it is still 0 that we set it originally, initially. If it remains 0, that means what? It was not set to 1 in any stage of the division. That means what? No divisor was found in between this range. So we can say that it is a prime number. Otherwise, it is not a prime number. So with this, I think I've shown you a lot of examples. With this, I complete my lecture session today. Thank you very much.